Hello everyone. So after going a quick description onto linear regression, I want to take this quick time to describe a little bit more about how we can tell whether or not there's a good fit in our data. And now, if you want some more background on this, please look at the slides I posted online to give you a little bit more background on how to interpret what's happening and how we can get a good regression. So just to touch base, if let's say we have this raw data as a data set, and I intentionally created this so there's a good amount of noise so that we can describe what it is we're talking about. Now you've probably already seen we can add a trend line, we can display the equation on the chart. Let's not set it to 0. And we can display the equation on the chart and add a R-squared value. And you'll get this very nice result where you see this R-squared value for the regression coefficient. And I'm sure you are all familiar with the idea that, and you've probably been told before, that the closer this is to 1, the better the data is, the better the model describes the data. So, and that's a given. That's what we call the regression coefficient. Well, I want to explain a little bit where this comes from and how you can actually calculate this yourself and what it means more fundamentally. And so, in brief, let's go back to what's actually happening in this model. Remember, regression is simply minimizing the sum of square errors. Minimizing that, and the best fit is going to be the point at which that sum of squared error value is as close to 0 as possible. Now, so we can create that in this system by defining the slope and the intercept. And so by the regression analysis, we can put it as 1.164 or 1.5037 for this. And we can create a column of Y model for the raw data, which is just going to be based off of the actual equation that we have. So it's going to be X times our slope, F4, plus the intercept. And that's our Y model data. Control D. And then we can add a column square errors. And we can actually take this, subtract this from this squared, go down, Control D, and we'll get some, our SSE. Let's define that as SSE and get our sum, and bring this up. There you go. And so we have this. And I intentionally put these as bold before so you can kind of see what's going on. But as you can see, we have a squared error and we have a low value, and the closer this is to 0, theoretically the better the fit is. But now you'll notice that R-squared is actually 0.82, so it's not that great of a fit because there's a lot of scatter in the data. And I'm sure some of you would say, arguably, and a good justification is to say, well, if this is 0, it's the best fit we can have, right? So why don't we just use the sum of squared errors as our goodness of fit and say, when this is closer to 0, the better it is. Well, the problem with that approach is that this sum of squared errors is going to be highly dependent upon just what the magnitude of numbers is that we're playing with. If, for example, we're varying from 1 to 1.7, 1.5 to 1.7, then clearly the range of data that we're having is very, very small. And so the sum of squared errors, even for a terrible fit, isn't going to be that large. As long as it goes through the data points, there's going to be a pretty small number, right? So, and you can kind of see this is true, that if we just took this data, I'm going to temporarily bring this out here, and if we just happen to multiply by 10 here, times 10, and brought this down, you can see our R-squared didn't vary, but the sum of squared errors became much, much worse, right? But the model fit is just all a magnitude of 10 greater, right? Everything else multiplied by 10. So we have to have some other metric by which we can try to normalize this so that we're not dependent on the absolute values of the data that we have. And so enters this other concept that we have, and that's going to be the sum of squared total. And this is abbreviates as SST. And what that is it's saying, well, in the data, raw data, in our y-axis that we have, the data, how it spreads here, that sum of squared totals, the variation is going to increase dramatically as the variation from the one data point all the way to the other data point, the range at which it scatters, increases. And so how can we find it? Well, the easiest way to do it is to say, well, what's the average y value? What's the midpoint of all the y's? And then how far is every data point away from that y average. And then we can divide SSE by that value and get our sum of squared total. So, and that's what we can do here. So we can get our square total. And now this expression and these equations are given on the PowerPoint slide. So I will, so please refer to that in this in this explanation. I'll bring that up really quickly. But here you can see it's on slide 6, or no, slide 7. Or I'm sorry, slide 9 of the PowerPoint slides, that you can see where this equation of sum of squared total is given. So, but how can we find that? Well, we can define an average, let's say mean y value, and we can define this as equal to the average y. And this is the average y, not for the model, but for the raw actual data. We'll have an average value. So that's just, this is just the mean y, and I'm going to put it over here as a constant. And then I'll just say the sum of squared total value is going to be y of our raw data minus this average value squared. Oops, cancel. Squared. And we'll bring this down. Control D. We can copy and paste just so you can see it's the sum of those values. And you can see now right away that this value is very, very small, right? It's because the range at which it's scattering is not very big. But we can define r squared, and r squared is given as 1 minus the sum of squared errors divided by sum of squared total. So if we say 1 minus sum of squared errors divided by this, then we'll get our r squared value of, and I'll color this green just so we can highlight it, of 0.8257. And that's what Excel has also calculated as our r squared value. And this will scale regardless of the magnitude of this raw data that we have here. So if I was to say copy this, bring this over here, bring that out, and then simply said, okay, let's go ahead and give this value as a magnitude of 10 here, and brought this all down. And actually I forgot, we got a 11.634 and 15.037. The square errors increased by 10, everything increased by 10, but our r squared values did not change. In other words, this was proportional, and we no longer are dependent on the magnitude of data. And this is an advantage of the r squared value, and why we use this as our metric for saying goodness of fit, or how good our data is, how good the model fits the data, rather than just the sum of squared error final number. One other point to note, actually the sum of squared errors does give you another significance to this, and that's by a percentage. What we can now say, actually, in this sum of squared errors, is we can say that effectively it's the percentage of the scatter in the data, how much the data varies around the model, how much of that scatter in the data is described by the model, and how much isn't described by the model. In other words, we can say that 82% of the data, or 82.7% of the data, is the model describes the change in data that we see. Conversely, we can say that 1 minus this value, or 17.2% of the of the scatter in the data is not described by the model, meaning that we are not picking up 17% of the nuance of the trends and so forth that is described. That 17% may come from noise or from imperfections in how we collected data, or it may come from a phenomenon that's fundamental to the system that we're not capturing by simply a linear equation. And either interpretation is true and valid for us to note. And so that is, I guess, a good ending point of just describing how goodness of fit, or how good the model fit is using r squared values. I encourage you to go ahead and look at the slides and look in a little bit more detail. The same information is explained here. We do describe some of the definitions of how a squared can be used to describe what the total variation that exists, why 0.585 is 85, why the r squared value is what's explained by the data, what's not explained by the data. And also in the slides, it gives another approach, another related measure of goodness of fit, an example of Pearson's correlation coefficient. These are just another way of getting at the data. Unfortunately, statistics, there are lots of ways to calculate goodness of fit, but this is another measure. It's given by this equation here, and it describes it's a range from -1 to 1. But the nice thing about it is when you square the Pearson's correlation coefficient, it will give you also R-squared. And so it's just, again, another way of getting at goodness of fit from another statistical approach. So thank you for your time, and we will continue on with going into other approaches to linear regression analysis. So, and thank you again.